Hello, this is Stereochemistry 3, Part 1. Again, as you can see in the slide, we need to keep in mind that enantiomers have the same boiling points, melting points, and solubilities. They have different arrangements in space of groups bonded to the asymmetric carbon, and that's why we have R and S configurations. And also enantiomers interact with polarized light differently. We're going to see that on the next slide. And that is one way of distinguishing enantiomers. So let's take a look at that. Okay, chiral compounds are optically active. They rotate the plane of polarized light. Normal light rotates and oscillates in a wave-like manner in all directions, as you can see right here with normal light. Notice in all directions. Plane polarized light, which is right here, oscillates in a single plane. Chemists notice that when polarized light passes through a solution of achiral molecules, the light emerges from the solution with its plane of polarization unchanged. An achiral compound does not rotate the plane of polarization. Therefore, it's optically inactive. But, as you can see in this diagram, when polarized light passes through a solution of a chiral compound, notice it says sample tube containing a chiral compound, the light emerges with its plane of polarization changed. Therefore, a chiral compound rotates the plane of polarization. It will rotate it clockwise or it will rotate it counterclockwise. One enantiomer rotates it clockwise. Its mirror image will rotate it in the same amount counterclockwise. Therefore, they are optically active. So again, you can see in this display here, a light source, like a light bulb, will provide normal light that oscillates in all directions. If it passes through a polarizer, then we have plane polarized light that oscillates in one direction. If it then passes through a sample tube containing a chiral compound, the light rays are actually rotated, bended. The plane of polarization has been rotated if it's a chiral compound. Achiral compounds do not rotate the plane of polarized light. They are optically inactive. If the plane of polarization is rotated clockwise, it is dextrorotatory, indicated by a plus sign. If it is rotated counterclockwise, it is levorotatory, indicated by a negative sign. Dextro means to the right in Latin, and levo means to the left in Latin. R and S are not the same as D and L. Some R configurations are plus and some are minus. Now, sometimes we will say D is somewhat equivalent to a plus, which means to the right, clockwise, and L is sometimes equivalent to a negative sign that's used to mean counterclockwise and to the left. Okay, let's look at this a little further. Here we go. A polarizer measures the degree of optical rotation of a compound. And you can see here the equation for the observed rotation, alpha. And the components of this equation are spelled out here. Of course, this is known as specific rotation. T is the temp in degrees Celsius. Lambda is the wavelength. Alpha is the measured rotation in degrees. And L is the path length in decimeters. And little c is the concentration in grams per milliliter. Each optically active compound has a characteristic specific rotation. So it's a specific characteristic of a compound. One enantiomer of 2-methyl-1-butanol has a specific rotation of plus 5.75 degrees. Its mirror image rotates the plane of polarization the same amount, but in the opposite direction. So the specific rotation of the other enantiomer is minus 5.75 degrees. Now, how can we tell if a compound is plus or minus? We can tell if a compound has R or S by looking at its structure. The only way we can tell if it is dextrorotatory plus or levorotatory negative is to put it in a polarimeter. Okay, let's look at 4 definitions. Okay, a racemic mixture is not optically active. They do not rotate the plane of polarized light. Every molecule that rotates the plane in one direction is matched by another molecule that rotates it in the opposite direction. So the symbol plus is used to symbolize a racemic mixture. Actually, the symbol plus with a negative sign also together at the same time is used to illustrate a racemic mixture. An enantiomerically pure sample has only one enantiomer present and it has an observed specific rotation like plus 23.1 degrees. If the specific rotation is 0 degrees, then it is a racemic mixture. Okay, third definition, optical purity is actually given on this slide. If the observed rotation equals the rotation of the pure enantiomer, then optical purity is 1, obviously. If the observed specific rotation equals specific rotation of the pure enantiomer, then we have an optical purity of 1. Also, enantiomeric excess is another definition. Enantiomeric excess is observed specific rotation divided by specific rotation of the pure enantiomer times 100 degrees, 100% rather. So enantiomeric excess tells us how much of an excess an enantiomer is in the mixture. For example, if the mixture has 60% enantiomeric excess in S, 60% of the mixture is excess S enantiomer, and 40% is a racemic mixture. Half of the racemic mixture plus the amount of excess S enantiomers equals the amount of S present in the mixture. So it would be 60 plus 1/2 of 40, which actually adds up to 80. So 80% of the mixture is S and 20% is R. Okay, let's look at this. How many stereoisomers can exist? We've seen this before. It depends on the number of chiral carbons or the asymmetric carbons in the molecule. Isomers with more than one chiral carbon have a maximum of 2 to the n stereoisomers. This example, in this molecule, notice there are 2 asymmetric carbons. Therefore, there's 2 raised to the second power, or 4 possible stereoisomers, and they're listed here. If we were to call this one 1, 2, 3, and 4, you can see. Notice that this is the perspective formula of the stereoisomers of 3-chloro-2-butanol using the staggered display. And I mentioned earlier that staggered cannot be used to actually see erythro and threo easily in this display. However, with eclipsed, we can see and understand erythro and threo. A compound can have a maximum of 2 to the n stereoisomers where n equals the number of asymmetric carbons. This is true as long as there are no other stereoisomers present, such as carbons where the interchange of 2 groups converts a cis isomer to a trans isomer or a Z isomer to an E isomer. 3-chloro-2-butanol is used as an example in this slide. Since it has 2 asymmetric carbons, it has 4 stereoisomers. In the models, green is chlorine and red is oxygen atoms. 1 through 4 are 4 stereoisomers. 1 and 2 are non-superimposable mirror images and are therefore enantiomers. Same can be said for 3 and 4. 1 and 3, 1 and 4, 2 and 3, and 2 and 4 are not identical and they are not mirror images. Therefore, they are diastomers. Diastomers are stereoisomers that are not enantiomers. So let's look further at this definition of stereoisomers and looking at them as enantiomers or diastomers. Enantiomers, as you remember, have identical physical and chemical properties. Diastomers have different physical and chemical properties, different chemical rates, chemical reaction rates. And back to erythro and threo. These are two general terms. They can be demonstrated if we put 3-chloro-2-butanol in the eclipsed form. And here we are back with the eclipsed form, and you can see it with this display. We have 2 to the n equal 4 stereoisomers, 1 and 2, 3 and 4 are enantiomers. 1 and 3, 1 and 4, 2 and 3, 2 and 4 are diastomers because they are not mirror images. As you can see, those with similar groups on the same side of the carbon chain are erythro enantiomers. Or you may see 2 hydrogens coming out towards us, as in this display here. Those with similar groups on opposite sides are called threo, as you can see in this display. 1 hydrogen towards us and the other away from us also is a way of looking at it. There's 1 towards us, 1 away from us, 1 towards us, 1 away from us. So, with erythro, we have similar groups on the same side of the chain. With threo, we have 1 hydrogen towards us and the other hydrogen away from us. These two are non-superimposable mirror images, so they're enantiomers. These over here are non-superimposable mirror images and are also enantiomers, 3 and 4. Now, erythro and threo, often you'll hear that later when you study monosaccharides, but erythros, sugars, have OH groups on the same side of their carbon chains, as you'll see in biochemistry. Threose sugars have OH groups on different sides of their carbon chains. And again, you'll see this later when you get into biochemistry. Okay, let's stop at this point right here.